Stanford, who speaks on homogeneous structures in subset sums. So please go ahead.
Great. Thank you. So thank you everyone for coming. So what I will discuss today are based on all based on joint work with David Cullen and my advisor, Jacob Fox. So the material here are drawn from 2 papers that we uploaded last year, as well as one upcoming paper that hasn't been made available yet. And as the title says, I will discuss structures that we can find in a set of subset sums under certain conditions. And then we will discuss the many applications that our technique will give. So let's just start with the main object of the talk, that is a set of subset sums. So given any set A, finite or infinite, of integers, we will define the set of subset sums to be simply the set of all integers that can be represented by a sum of finitely many distinct elements from A. So simply we go over all subsets S of A and then collect all of the sum of elements from the subset S. Okay, so of course we can generalize this definition to A being a subset of any abelian group, for example, a set of integers or real numbers. Okay, so as I said, our main focus is to find large structures inside a set of subset sums, and the first one that we will focus on will be on long arithmetic progressions in subset sums. And to start, I will start with a seminal result of Zemmery and Wu. So they show that if we have a subset A of the integers from 1 to n, and the size of A is sufficiently large, and so here it means at least some large constant times square root of n, then the set of subset sums sigma of A must necessarily contain a long arithmetic progression. So an arithmetic progression of length at least n. And we can see that this is tight because, for example, if we just take the first little c times square root n many elements, then we cannot find an arithmetic progression of length larger than n, but also there are other construction that shows that this threshold is tight in many interesting ways. So I won't have time to go into that details, but now let me remark that, okay, so in fact, for many applications that we will soon see, we'll want a slightly stronger notion of the arithmetic progression, and that's the homogeneous progression. So we say that an arithmetic progression of this form is homogeneous if the common difference D is a divisor of the starting term x. Or in other words, if we extend this progression infinitely to the right and to the left, then this infinite progression must necessarily go through 0 for the arithmetic progression to be called homogeneous. Now, Freiman and Sarkozy much earlier actually proved that if we have a large subset of the interval from 1 to n, and large here means at least square root n times log n, so there's an additional logarithmic factor compared to the threshold of Zemmery and Wu's theorem, then the set of subset sums sigma of A will contain a long homogeneous progression. So, so this one gives a slightly stronger structure, but at the cost of a slightly weaker threshold. And as you see, it's a lot of work to go from this threshold of square root n log n to square root n, as in Zemmery and Wu's theorem. Zemmery and Wu's theorem has quite a difficult proof. And the first result of us that I will mention is that we can obtain a common strengthening of the result of Zemmery and Wu and the result of Freiman and Sarkozy. So we can show that if we have a subset of 1 to n with size at least some constant times square root of n, then the set of subset sum will contain a long homogeneous arithmetic progression. So a homogeneous progression of length at least n. Okay, and in fact, our proof is quite short. So the proof of this result using the framework that I will discuss soon takes about 5 pages. So it gives a quite short result that recovers the strengthening of these 2 very nice theorems. Okay, so as I mentioned already several times, this homogeneity turns out to be quite useful for some applications. So let me discuss some of these quick applications. The first application is on non-averaging sets. So this is a question of Strauss back in the 70s and also reiterated by Edish. So a subset A from 1 to n is said to be non-averaging if no element of A can be represented as an average of 2 or more elements of A. So if we have a set A that doesn't contain any non-trivial arithmetic progression, that's the same as saying that no element of A is the average of 2 other elements of A. And Roth's theorem tells us that such a set must have size sublinear in n. And there are also longer other generalization of Roth's theorem, for example, when we put in more variables that just corresponding to the constraint that no element is the average of k other elements of the set A. And here for this notion of being non-averaging set, we are just we are putting no constraint on the number of elements that we are allowed to take in the average, and we want to force that no element of the set A is an average of some other subset of A. Okay, so so early results of Adish and Sarkozy and shows an upper bound on the size of the largest non-averaging subset of n to be about square root n log n, and it's no coincidence because it essentially uses the bound Freiman and Sarkozy that we saw earlier. And also there's a construction of Bosme that gives a lower bound of n to the quarter. So we see that the behavior of the upper bound is already different from what we see in Ross theorem or when we only allow a constant number of elements to be involved in the average. But so, okay, so roughly we know that the size of the largest non-averaging set is a power of n, that's roughly between a quarter and a half. And an immediate corollary of our previous result, when we produce a homogeneous progression and not just a progression, is that we can improve this upper bound from square root n log n to about square root of n. Now, we'll see later that in our upcoming work, we develop a multidimensional generalization of the theorem we have on the previous slide, and that will actually allow us to prove an upper bound on h of n that is a power of n, which is strictly less than 1/2. So the bound square root of n is not tight, and the power we obtain is about square root 2 minus 1. And yeah, we'll see that later towards the end of the talk. Okay. So that's one nice application where we see that being homogeneous is useful. And to discuss the next application, let me just quickly mention a small strengthening of the result that I mentioned at the beginning. So in fact, we don't need to sum many elements of A in order to obtain this long homogeneous arithmetic progression. So based on the size of the set A, we only need to sum a constant times n over A, many elements. And clearly this bound is also tight for trivial reasons. So just for the notation, sigma k of A just means the set of sums that the set of sums of subsets of sizes most k of A. So we are only allowed to sum up to k elements from A. And using this small strengthening, we can obtain essentially the complete answer to the following question of Adish and Graham. So this is an extremal question. And the question is this: so we fix n and fix some m that is larger than n. The question is, what is the maximum size of a subset of 1 through n, such that no subset sum of this set is equal to m? So we want to avoid m as a subset sum, and we want to find the largest, the extremal set with this property. And so this question was investigated by many people before, and Alon and Freiman proved the following very nice exact bound in the range where m is large compared to n. So they proved that Gn in this range, this largest size Gnm is actually exactly equal to the following function. And this function here is roughly n over fnd of m, where fnd of m is the smallest positive integer, which is not a divisor of m. So to see that you should get some bound like this is quite easy, right? Because if you just take the set A to contain of all multiples of this integer fnd of m, then suddenly no sum from this set can contain m, because any subset sum out of this set will be a multiple of fnd of m, and m is not a multiple of snd of m. So this stands for smallest non-divisor. And it's a cute exercise to try to prove that you can actually obtain a lower bound on G and M, so you can construct a set of this size, which will avoid a subset sum being equal to M. So the much harder direction is to prove an upper bound of this form. And Alon conjectured that, at least asymptotically, so G and M is always equal to 1 plus 0 of 1 times S and M. And that was resolved by Tran and Wood in 2009. So they showed that in essentially the entire range of M, we obtain this the following asymptotic bound on G and M. So this resolves Alon's conjecture. And our result is with quite a short proof from our theorem earlier on long homogeneous arithmetic progression in subset sum, is that we can determine exactly G and M to be equal to this function S and M we saw before in essentially the entire range of M. So and also we determine G and M asymptotically up to the largest interesting value of M, which is about n choose 2. So the main point here is that the answer will take on some different shape when you go beyond this threshold of n squared over 8 times log n squared roughly, and also when you go below n log n. So this threshold of c times n log n is actually tied up to the constant factor in order for this bound g and m being equal to s and m to be true. So essentially we determine the entire range where you can hope to have this nice exact bound. Okay, so all right, so I've mentioned the main theorem along homogeneous progression and 2 applications. So now let me tell you the general framework. So I think the framework is actually more useful than the result itself. So the main question here is, how can we construct long arithmetic progressions or homogeneous arithmetic progressions in the set of subset sums? And here's our general recipe to do it. So there's a general argument of 4 steps, and we'll see that on one step here is the most important one that I will emphasize on. So the strategy is this. First, we partition the set A into some constant number of parts, so into A1 up to AL, and usually it's useful to do this randomly or uniformly at random. And after that, for each of the smaller parts AI, we will partition it into 2 sets, AI prime and AI prime prime. And the main step is to show that for all elements little a in AI prime prime, the set of subset sums of AI prime modulo A is large. Okay. So I will remark later, this is exactly the main step in all of the applications. After that, we can use the result from step 2 in order to prove that the size of sigma of AI is large. And also usually in the applications, we can show that sigma of AI is trapped in some rather small interval. So we can actually conclude that sigma of AI is a dense subset of some interval. And in the last step, we have L sets here, each of them giving rise to a set of subset sums that is a dense subset of an interval. So we can then sum all of these dense subsets of intervals up, and we can then show that their sum set must necessarily contain a long interval itself. Okay, so there's some quick intuition that we can explain why we expect. So for example, to go from step 2 to step 3, one can just observe that if we have a set A, and you are going to add in an additional elements in A, then the size of the subset sum will have necessarily grows by at least the size of sigma of A modulo A. This is a quite easy but also useful observation. And using this, you can immediately obtain the result of step 3 from step 2. And the results of other steps are somewhat standard, so I won't go into the details, but yeah, so as I remarked, the main thing that we have to prove in the application is to prove the following guarantee in step 2. So we want to show a lower bound on the size of subset sums of a certain set modulo some number. So we translate from the setting of integers to some cyclic group. And this is the key step that we change from application to application. And as I said, the argument is quite flexible. And what it means is that if we know some additional additive constraints on the set A, then we can actually show improvement to the threshold in Zemirian-Rule's theorem. So I remarked earlier that the threshold of square root n in Zemirian-Rule's theorem is tight, but that is tight when we have essentially no constraint on the set A except for the lower bound on the size. But when we have some additional constraints, for example, that A is a subset of primes, then we can actually improve the bound, and that will be the key to some of the interesting applications that I will discuss next. So it turns out that, right, so in all of them, the only change will be in this step 2, and we'll see how we can modify step 2 to fit in the applications. Okay, so just to discuss some more interesting applications of this framework, the first application that I will talk about is the notion. So there's a question on the size of AI prime prime and AI prime. So for us, because we ignore absolute constants in most places, we can, so ideally one wants AI prime prime to be, there's some trade-off here, but for us, we choose AI prime prime to be maybe an 8th fraction of the set AI, and AI prime to be the other 7/8 fraction. There's some flexibility here, and I think in general, one wants AI prime prime to be somewhat small compared to AI prime, but not too small. Okay, so the next application I will discuss is about complete sequences. So this is also a classical topic. So a set of natural numbers is called complete if we can represent any sufficiently large positive integer as a sum of distinct elements from this sequence A. So in other words, if sigma of A contains all sufficiently large positive integers. So as some examples, the sequence of powers of 2 is complete. And the sequence of powers of 2, but you remove any one element will be not complete. So you immediately lose the ability to represent infinitely many integers. And there's a result of Sprague back in the 1940s is that the sequence of powers I to the k is complete for any k. And finally, there's a nice result of Birch that the sequence of p to the I times q to the j for two coprime p and q is also a complete sequence. Now, as we saw, complete sequence can be quite fragile. So if we remove some elements from the complete sequence, we may immediately lose the ability to represent many integers. So Burr and Edish coined the following notion of being robustly complete. So a sequence is called R Ramsey complete if whenever we partition the sequence into R sets, there is always all sufficiently large integer must be contained in the union of the subset sums of these color classes AI. So the other way you can think about it is that no matter how you R color the sequence A, every sufficiently large positive integer, it can still be written as a monochromatic subset sum. Okay, so there's a question about the result of Birch. So in fact, it's not because so for the result of Sprague, the sequence is changing with I and the exponent is k. K is fixed at the result of Birch. We are fixing the base p and q, but the exponents are changing. So this is actually a much sparser sequence than the sequence of polynomial values. Okay. Right. So Burr and Edish proved that there are quite sparse two Ramsey complete sequences. So we can select a sequence such that there are only about log n cubed elements up to n, and that is two Ramsey complete. They also show that such a sequence cannot be much sparser. So we need at least about constant times log n squared many elements up to n for infinitely many n. And they asked the following two questions. So can we improve these bounds for the two color case? And also can we extend it to the R color case? So their construction only works for two colors. It's actually an explicit construction using powers of 2. So, and it's reiterated several times. In fact, Edish even offered monetary awards to these two problems. And our first main result is we obtain a complete answer to these two questions. So in fact, for any R, we can show that there exists an R Ramsey complete sequence with only about R times log n squared elements up to n. So we see that this dependency on n is tight based on the lower bound of Burr and Edish, but in fact, we can also show that this bound is tight in both dependency on n and dependency on R. So we can show that if we have an R Ramsey complete sequence, then for infinitely many n, we need to have that at least R times log n squared many elements up to n. Okay, so the main lemma in this in proving the theorem, so I would just quickly discuss the proof and how it fits in with the framework. So the main lemma is the following one. So we want to show that we can select about logarithmically many elements from a dyadic interval from x to 2x, such that if we select any sufficiently large subset of the set A that we have here, then the set of subset sum of the subset A prime must contain a long interval. And one can show that once we have this result, then we can select an appropriate logarithmic size subset in each dyadic interval and take the union of all of them in order to construct the sparse Ramsey complete sequence that we saw earlier, that we wanted for the theorem. Okay, so how can we select the set A? It turns out that a good strategy here is to choose A at random, but just not uniformly at random because there are some divisibility constraints. So for example, if we choose A at random, then half of the elements will be even. And in particular, we can, if we select just all of the even elements from A, then we cannot hope that the set of subset sums contain a long interval. So in order to avoid these divisibility constraints, we will choose A as a sequence of uniformly and independently chosen elements with no small prime factor. Okay, and it turns out that after that, with a simple union bound, we can apply the framework. And the only step in the framework that we need to work hard for is step 2, as I mentioned earlier. And in this case, it takes the form of the particular key lemma. So the key lemma shows that if we choose a constant times log x, uniform and independent elements from the dyadic interval from x to 2x with no small prime factor, then the set of subset sums of this chosen sequence taken modulo m for essentially any m will have to be large, will have to be at least x over 4. So we would usually choose m to be from the same dyadic interval from x to 2x, so we can see that this bound is actually typed up to the constant factor. And how do we do this? Let me just remark, because we actually for step 2, we also have a strategy that is used over and over in all of our results. In order to show that the set of subset sums mod m is large, our strategy is to grow the set of subset sums mod m essentially greedily or iteratively. So we'll start with the empty set, and then in every step, we will take the set Si and put in some element Ai so that the set of subset sums grow a significant amount. So we want to choose Ai so that this one is maximized. So it's just a greedy procedure. And it turns out that when this growth in the set of subset sums is too small, then we can show that many of the elements then we can show that there are many bad elements Ai for which the inclusion of Ai in the subset sum doesn't grow the subset sum by a large amount. And it turns out that the set of those bad elements will have a very strong additive structure. So we can essentially sum them up. And in the end, we in analyzing the bad elements Ai, where the growth of the subset sum coming from adding Ai is too small, we can translate the question about trying to bound the size of the subset sum or sum of distinct element to a question about multifold subset. And for this, we actually know much more. We know very strong inverse results, and that will help us finish usually quite easily. So essentially, within step 2, the main strategy is to reduce something that we want to understand about subset sums, which is quite hard, into something about multifold subsets, which we have many available tools. Okay, so I can see that I'm running out of time, so I'll be a little bit quick to get to the high dimensional results. So it turns out that we can also show a much stronger result where we can construct Ramsey complete sequence of polynomial values. Oh, wow. So I was here. Yeah, so previously we choose out a Ramsey complete sequence using any possible integer values. But what if we constrain that we are only allowed to use, for example, perfect squares? It turns out that we can still show that we can construct a Ramsey complete sequence consisting of only polynomial values. Furthermore, we can actually construct such a sequence that is essentially as sparse as possible. So this is the same dependency on R and N that we saw when we have no polynomial constraint. So this answers another question of Burt and Edish. So let me skip this Ramsey type question on representing on monochromatic subset sums. And so the key point of this is to show you that this is just a corollary of another result of ours that gives an improvement on the result of Zamiri and Wu, where we have the additional constraint on the set A, for example, that A is a set of primes. So if you recall, the threshold for containing a long interval or arithmetic progression from before is square root n. For the size of A has to be at least square root n. Turns out that if A is a set of primes, then you can go much below square root of n. And you know how much you can go is the bound in this lemma that I won't go into further details. And the proof of this is using the same key framework. And in analyzing step 2, as I mentioned before, we can pass from subset sums to multifold subsets, and then we can use inverse results in additive combinatorics. We also use here a version of the Hilbert sieve. Okay, so let me just quickly in the last 2 minutes go over the results, the new results that we have for higher dimensional analogs of the theorem from before. So Zamiri and Wu in another very nice paper proved the following higher dimensional generalization of the result we had. So they show that if the set A have size at least n to the 1 over k, then sigma of A will contain a large generalized arithmetic progression, a large proper generalized arithmetic progression. And again, we can define a notion of being homogeneous for gaps, and we can show that, and we can obtain this following strengthening of the result of Zamiri and Wu. So at exactly the same threshold on the size of A, we can obtain a large, not only proper, but also homogeneous generalized arithmetic progression. And in fact, we have much stronger results. So let me just very quickly describe this. So if we have a set A that is polynomially large subset of the interval from 1 to n, and we have some number S that is at least polynomially large in M, then we can show that we have a large constant fraction of A hat, that is contained in a generalized arithmetic progression P. And furthermore, we can show that sigma of A hat, which is trivially contained in the size of A, in this multiple of the generalized arithmetic progression P, is actually also containing some constant multiple of this large generalized arithmetic progression, A hat times P. In particular, up to this constant here, this result is obviously tight. So we obtain quite precise control on the structure of the set of subset sums. And using that, this is one of the key tools that allow us to obtain the bound I mentioned earlier, that we obtain a polynomial improvement on the size of the largest non-averaging subset from 1 to n. Okay, so with that, I will conclude the talk. Thank you.
Thank you very much.